Hello everyone and welcome to this next tutorial in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last lecture we have finished our discussion of Gaussian process regression, and that came after a detailed discussion on decision trees, bagging, random forests, boosting, including various types of boosting like adaptive boosting and gradient boosting. In between we also studied the support vector machine formalism, which could be used for both classification as well as regression. So in today's tutorial we will learn how to implement these algorithms using Python, and we will do so for two different interesting data sets drawn from various core engineering disciplines. And before we start on this tutorial focused on decision trees, boosting, support vector machines as well as Gaussian process regression, I would like to take a moment to thank my hardworking teaching assistants Dr. Manas Sharma, Shivam Chaturvedi, Manasi Lavekar and Amar Krishna Gopinath. They are really helping a lot with this course, including with the tutorials as well. So thank you. So getting started with today's tutorial, it is going to be all about supervised machine learning with Python. As you know, supervised machine learning is where we have data with labels and we are trying to predict these labels. So those labels could either be a continuous variable, in which case it is called a regression problem, or they could be discrete values, in which case it becomes a classification problem, right. So this tutorial demonstrates various supervised machine learning techniques focusing on tree based methods, support vector machines and Gaussian process regression using Python, and we will cover both classification as well as regression models. These are the topics that we will be studying today. The first thing we will be looking at is a simple decision tree model for interpretable modeling, interpretable machine learning. We will then move on to random forests for ensemble learning, wherein the outputs of various trees are aggregated together to make a prediction. So that is random forests using the technique of bagging. And then as we move on to boosting, we will talk about two different libraries called XGBoost and LightGBM. We will also look at CatBoost for high performance gradient boosting, and then we will look at feature importance via the Shapley additive explanations method to explain the importance of various features and to understand the model predictions, and that will complete the first data set. So the first data set will be derived from materials engineering, wherein we will try to predict whether a material is a metal or not. So as you know, metallic materials are very important in various applications, including in semiconductor devices where they are used to make electrical connects, low resistivity connects, and even electrical and electronics engineers may be interested in knowing whether a material is metallic or it is a semiconductor insulator. Then we will switch gears, we will move to a data set from civil engineering, wherein we will try to predict the strength of a concrete mixture, and for that we will use Gaussian process regression. In between we will also look at support vector machines, wherein we will apply the same materials engineering data set, but you will see that SPMs do not perform as well as some of these more modern methods. If you try to see the chronology of machine learning, support vector machines came much earlier as compared to things like gradient boosting, which has only been there for about 10 years or so in terms of these libraries XGBoost and LightGBM. So let us go ahead and get started. The first data set, like I mentioned, will employ decision trees in supervised learning and use it for materials informatics, right. So what is materials informatics? Materials informatics is when you are trying to use information or features regarding materials to predict their properties and therefore to establish structure, property, performance relationships, right. So some kind of processing, structure, property relationships. So these have become very important in engineering. So how you process a material determines what is the structure of the material, right, and then the structure determines the properties of interest, and then the properties determine the performance of the material, right, in various core engineering applications. So, these kind of relationships are very hard to get by, right. You either need to do a lot of careful experiments or very painstaking simulations, but once that has been done through the use of machine learning, you can have very efficient algorithms to predict processing structure, property, performance relationships. Okay. So, this particular tutorial is going to examine how decision tree based models can be applied to a material science classification task, and we will focus on predicting whether a material is metallic or not using something known as the MatBench is metal dataset. So, I will explain what is MatBench. MatBench is an automated leaderboard for benchmarking state of the art machine learning algorithms for predicting a diverse set of solid materials properties, right. So, this leaderboard concept is very popular in machine learning. As you know, the performance of an ML model is quantified by how well it does on the test set. So, we use error metrics like the mean absolute error or the R squared or root mean squared error and so on. So, these leaderboards tabulate the output metrics, right, the test metrics for various machine learning models, and then you can compare which models are the best. So, there are leaderboards for various types of machine learning applications, right, in various engineering and science disciplines, and MatBench is one such leaderboard which is focused on solid materials properties. Okay. So, based on this data set, what all will we cover in today's tutorial? We will look at basic decision trees using scikit-learn. Then we will look at random forests, which employs the bagging ensemble. Bagging, if you remember, is bootstrap plus aggregation. Bootstrap is making data sets with sampling with replacement, and then aggregation is just putting together the prediction of multiple trees. Then we will switch gears and move on to boosting, including the scikit-learn gradient boosting, XGBoost, LightGBM and CatBoost, and we will use the Shapley additive explanation SHAP values for interpreting the model predictions and the feature importance. Now, where are the features coming from? The features in this case are the chemical composition of the materials derived from these so called MAGPIE descriptors. MAGPIE is a short form for materials agnostic platform for informatics and exploration, right. So, these kind of features are very popular for materials and they enable us to train interpretable models in real world informatics settings. Okay. So, of course, the prerequisites involve installing necessary packages. Now, you will notice that some of these codes do get cut off at the end, but do not worry, we will be sharing the Python notebooks, the Jupyter notebooks, which you can load on your own computers, and you will be able to see all the code and you will be able to execute it line by line. So, I encourage you to download the Jupyter notebook for this tutorial from the NPTEL website, and then you will be able to do all the things that we have to do. So, some of the packages of course include NumPy, Pandas for accessing Excel files, Matplotlib for plotting, Seaborn for data visualization, scikit-learn for basic ML models, SHAP for feature importance analysis, and then of course XGBoost, LightGBM, CatBoost. You also need libraries for Gaussian process regression and so on. Okay. So, the first thing of course is to load the data and to explore it a little bit. So, what we will do is we will use this MatBench is metal data set. It contains 4,900 materials or so with their compositions and a binary label indicating whether the material is metallic, true, or non-metallic, false. So, you can see that this is a binary classification problem that we are going to tackle in this particular tutorial. Okay, so let us go ahead with this. So, what are the features that are available? The features are computed using the MAGPIE descriptors, and these are derived from the materials compositions. So, for example, the mean atomic number of the elements in the material, the mean electronegativity, the atomic radius, and so on and so forth. So, those are the features we will be using. Then in terms of the target variable, we want to predict a binary classification label, which is essentially whether the material under consideration is it a metal or not. So, we want to predict a true or false. So, if it is true, that means it is class 2, it is a metal, and if it is false, it is class 1, it is a non-metal, right. Now, we want to predict whether a material is a metal based on its elemental composition. Like I said, there can be various use cases for this. Metals of course have various desirable properties. They have very high melting points, they have very low resistivities, they have high conductivities, whether it is thermal or electrical conductivity. So if you are searching for a material for a specific application, and you can be an electrical engineer, electronics engineer, civil engineer, chemical engineer, materials engineer or mechanical engineer, but there are various scenarios in core engineering wherein you want to understand the properties of a material and whether that material is a metallic or not. So that is where this particular scenario is going to be really useful. Okay. Now like we already discussed, the data source for this is the MathBench IsMetal leaderboard, and you can easily access this if you go online. I have also given the link here, it is available at mathbench.materialsproject.org where there are various other leaderboards also which can be accessed. Okay. So now what we are doing here first is to load the data set. If you see here, I have a small snippet of code which essentially tells the Python to ignore these warnings. I recommend that you do not do this, right. Why we have done this here is so that the tutorial reads smoothly and we do not see pages and pages of text where these warnings are visible, but I recommend that you do not include these commands so that you actually see the warnings and you see the messages that Python is trying to tell you, so that you can improve upon what is happening. Okay, so what is the way to implement this? You have to import from mathminer.datasets the load data set, and then from mathminer.featureizers.composition you have to import element property. Alright, so these of course need to be installed. So you will have to execute this particular command which you can copy from the Python Jupyter notebook and then paste into the notebook on your machine, or just execute the notebook as it is. Okay, so then we are also importing pandas for working with Excel files, and then this PyMatGen is a very useful library in materials. So it is a Python materials library, and I strongly encourage you, if you are a materials engineer or other allied disciplines like chemical or mechanical engineering or civil engineering, you can look into this particular library. It is very useful when you want to work with materials. Okay. Then of course we have to load the data set, that is quite straightforward, and we have chosen this particular data set, the MathBench experimental IsMetal data set, and then we convert the composition strings to composition objects, and finally we apply MacPy style element features, right. Ultimately, as we had discussed, we want to use the elemental features to understand, right, how the features are related to the property, right, whether it is metallic or not. Okay, so this is all part of data processing. I am dropping the composition object here because I do not need it for my machine learning, and then these are the final features and the labels, right. So X, this is the matrix of data where the rows are each data point and the columns are basically your features, and your target variable is very simple. From the data frame df, I have simply extracted the IsMetal property. So and on doing that, I have tried to print the shape of x and y, which will tell you how many data points are there and how many features are there. Okay, so this is the kind of messages you will get when it is running, and it will take some time to import all the data, perhaps a couple of minutes, depends on the internet speed, and then once you have done, you can look at the shape, right. So this tells us that there are about 4900 data points and there is about 132 features. So the number of data points is much larger than the number of features, which is good. Which means that we can develop robust models. Now if you have a number of features that are close to the number of data points, that is a bit of a problem, because then your model may be very noisy, right. It may not learn the exact relationships, and depending on the training data it may not be actually generalizable when you have other kinds of scenarios. Okay, so now let us visualize the relationships between the key compositional features and the IsMetal label using pair plots, and for these pair plots we will use the Seaborn library, and this Seaborn library is something that you have actually seen in one of the previous tutorials. If you go back, we had actually used this to do some data visualization already, so it should not be new to you. You must have had some experience with Seaborn. Okay, so now we import matplotlib also to make plots, and then these are some of the features that we want to visualize, right. So I am plotting the mean electronegativity, the mean atomic weight, the mean column, and the mean covalent radius. Now you will ask, I mean, what is meant by the word mean here? The word mean here, and I have explained this slightly below, let me go there, or maybe it is not here, but I can just explain it to you. Mean implies that we are taking the average of the property among all the elements in the compound, and this is compositionally weighted, right. So for example, if you have a compound like, this is just an example, Al2O3, what you will do is you will take 2/5, right. So there are 2 quantities of Al and then 3 quantities of oxygen. So the fraction of aluminum is actually 2/5. So you will take 2/5 of the feature of aluminum, and then you will take 3/5 of the feature of oxygen, and that will give you the mean feature. And this feature, if it is the electronegativity, then that means you are computing the mean electronegativity for Al2O3, and then mean atomic weight. Similarly, if you take the atomic weight of aluminum and the atomic weight of oxygen as FAL and FO, then you will get the mean atomic weight. By mean column, what I simply mean is you are taking the mean group in the periodic table. As you know, if you remember some chemistry, you have a periodic table of elements wherein there are rows which are called periods, and then there are columns which are called groups, and I am taking the mean value of this column. So let us say aluminum lies in a particular column of the periodic table, oxygen lies in another column of the periodic table. So I am taking the mean column based on the compositional weighting. Okay, so I hope you understand what we mean by the word mean here. Of course, electronegativity, atomic weight, covalent radius, that is the atomic radius, all these things are intuitive. By column, of course I have explained that it means the group or the column in the periodic table. Alright, so now we are creating a data frame for plotting. We have selected only these features because we do not want to be overwhelmed by all the data, and then we are just using this is metal as a map here, right. So true means metal, false means non-metal, alright, and then we can visualize this pair plot, right. So we are using Seaborn's pair plot function, it is a very effective function, and we are giving this data frame. If you remember, we had a data frame that included all the data, which was df, and now out of this df we have only selected some of these features. So that is called df plot, not df, and we are applying this pair plot function of Seaborn on the df plot data set, and then the color is decided by this is metal. So what this means, hue means color, so that means your true will be colored differently and false will be colored differently, and that is why you can see that there is some nice colors appearing in this Seaborn plot below. And this alpha, as you already know, that is the transparency, because we have points overlapping on each other, we do not want the points to get hidden, so that means that we are using a transparency of 60% when we are making this plot. And you know how to add titles overall for all the plots, that is with the subtitle command, and these attributes like font size and all you can tweak it. Alright, so these are the selected properties, and on the diagonal axis what you are seeing is a distribution of these properties and a distribution for metals, which is in blue color, and for non-metals in orange color. So that is really nice. So already you can see that if it is a metal, your electronegativity is slightly towards the left, and if you are a non-metal you are electronegativity is slightly towards the right, and that makes a lot of sense. Metals are electropositive in nature, they are not electronegative, so it makes sense that their electronegativity is peaking towards the left, and for non-metals is peaking towards the right. But of course there is you can't do much more quantitative analysis with this. It is good to understand and think what is going on, but of course at the end of the day you will need machine learning for this analysis. Okay. So then these same variables are also there on this x axis, the horizontal axis. So the second variable is mean atomic weight. So this scatter plot is for the mean electronegativity versus the mean atomic weight. So you can see that there is not so much of a strong correlation as there is for mean electronegativity and mean column. You can see that as the column number increases the electronegativity increases, and as the non-metallic character increases the mean column also increases. This also makes sense because if you remember or if you look up a periodic table as a chemist or if you are interested in this, you will see that all the metals are mostly towards the left and the non-metals are mostly towards the right. So it makes sense that there is a correlation between the mean electronegativity and the mean column number, and there is also correlation. You can see there is some clustering happening here wherein the non-metals are appearing towards the right and the metals towards the left. Now if you look at the last feature here, which is the covalent radius, you can see that there is actually a negative correlation between the electronegativity and the covalent radius, which means that as you increase the radius then it becomes more metallic. So these are some really nice and interesting insights that you can get from these kind of plots, and I highly encourage you to explore the capabilities of Seaborn. It is a very useful piece of Python library which can be used to create not only nice looking plots like this, but there is so much physics, so much depth and understanding that is behind all these plots. Okay, so I encourage you to open the Python Jupyter notebook yourself and spend time with some of these plots to try to understand why there are positive correlations for some of these and there are negative correlations for some of these others. Of course you will see that this covalent radius versus electronegativity, this plot is just a flipped version of this plot, so it is natural that it will look the other way, right. So this is electronegativity versus covalent radius, and then this is the other way. So you are just taking the reflection in the y equals x plane, so that is why it looks different. Okay, alright. So with that understanding we can conclude that both metallic and non-metallic materials exhibit distinct patterns across several compositionally weighted features. So the features we are defining are compositionally weighted features in the manner I had described a little while ago. Okay. So now before proceeding we will have to split the data set into a training part and a testing part. You know that this is the standard approach, and here we are using a test size of 0.3. For the random state you should look up the Jupyter notebook. I want to point out something here that we have actually used the stratified test train split, and that is very important when you are doing a classification problem. And I will tell you why that is important, because you can have certain classes dominating your data set, right, and that becomes a problem because of course then you can work with the balanced accuracy, but it is good to do stratified sampling so that you sample an equal number of metals and equal number of non-metals from your data set. If you do not do stratified sampling, then you risk having more let us say metals. If the fraction of metals is more in the data, then you will have more metals in the training as well as test set, and that can skew your metrics, but of course you do have something like the balanced accuracy to fix for that, but nothing better than already stratifying it. So how to implement the stratification, the code is getting hidden, so you should check in your own Python notebook that you can download. Okay. So the based on the 70-30 split, the training size is 3444 data points and the test is 1477 data points. There is of course 132 features. Now this is an important thing, that scaling is not necessary for tree based models, right. So if you look at things like linear regression, or neural networks or support vector machines, scaling of the variables is very important in many cases. And if you remember some of the tutorials, we have discussed the concept of a standard scaler, right, SCALER, standard scaler. And what this standard scaler does, you know that it makes the mean 0 and it makes the standard deviation 1, and that is nice because then all the variables are sort of on a similar range, and then the models work much better. But for decision trees, scaling is not necessary. Why is that? Because in a decision tree, if you remember, you just split the tree into 2 branches at every point, and that splitting is easy, right. You just pick a value and then all of it towards the left is one part of the tree, all of it to the right is another region of the tree. So for that reason, scaling is not necessary for tree based models, and things like decision trees, random forest, gradient boosting, XGBoost, light GBM, cat boost, they all split based on the feature threshold, not on distances or dot products, and they are invariant to monotonic transformations including standardization or normalization. But we do need scaling for other types of ML models like support vector machines, k nearest neighbors, which we are not covering in this course, but you are free to read up on it, then things like logistic regression, neural networks, Gaussian process regression, and so on. So therefore we will use scaling later for these models. Okay, so let us go ahead now and begin with our first model, which is a decision tree classifier, and I will do a brief recap of decision trees for you. You would remember that a decision tree is a supervised learning algorithm which can be useful for both classification and regression tasks. By now you very well know how a decision tree works. You split your data set into various regions, and once you reach a leaf node, you make a prediction based on the mean value for regression problem or the majority vote in that region for a classification problem. So decision trees work by recursively splitting the data set into subsets based on feature values that result in the highest information gain or the lowest impurity. And if you remember, we had actually by hand tried to train a decision stump, right, a decision tree with just one node. This was for predicting whether a material is a good solar cell candidate or not, and that was actually done by hand. But today we will use a different approach wherein we are trying to use Python to train these kind of models. So at each step the tree chooses the feature in the threshold that best separates the data using the criteria like Gini impurity or entropy, and it creates decision nodes and leaf nodes based on this split. Decision nodes are nodes where the split happens, and then leaf nodes are where you actually make a prediction, and this process is repeated recursively until a stopping condition is met. For example, you have exhausted the maximum depth, that is a hyperparameter, you have reached the minimum number of samples in one particular leaf and you have to stop. So these are all model hyperparameters, and cross validation should be used for fixing things like these. Alright, so this is just a very simple schematic of a decision tree to remind you. This is derived from this particular website, medium.com, decision tree in machine learning, simplifying complex decisions. Now you know that we typically do recursive binary splitting, but just for illustration we have used 3 splits here. Usually in all decision trees it is simplest to just do 2 splits, so that is something that you should remember. So this is trying to understand the risks to prevent a heart attack. It is based on age, right. First you are seeing whether the age is low or high, and then if you are more than 30, then if you are a smoker it is high risk, if you are not a smoker low risk, and then of course if you are less than 18 but your weight is high, then you are still high risk. So this is the kind of a logic. So as you can see, decision trees are really interpretable, they can very nicely be understood. Okay, so what are the key characteristics of a decision tree? They are interpretable, they are easy to visualize, and you can understand the logic behind the predictions. Why your point went into certain branches and what was the prediction that was made. They are still non-linear, they can capture complex decision boundaries. So although you are just splitting the tree based on different regions, they can capture non-linearities, unlike things like linear regression, and they are insensitive to feature scaling. So this is something we already discussed. So unlike models like support vector machine or KNNs, decision trees do not require you to standardize your features. However, they are prone to overfitting because you can keep on increasing the size of the tree till every point is just its own region, and then of course your training loss is 0, right, because if every point is its own region you will always predict the right answer for the train set, but in the test set you can fail miserably, and that is why decision trees are prone to overfitting. So, if you do not do proper regularization like limiting the depth of the tree, then trees can actually memorize your training data, which is of course not useful. We discussed the distinction between memorization and learning, right, that is based on whether you can predict your unseen data well. Now, let us train a decision tree classifier to predict whether a material is metallic or not. Okay. So, from sklearn.tree we are importing the decision tree classifier and plot tree. We are also importing things like the classification report, the confusion matrix and so on. For the entire code you can refer to your Jupyter notebook that you can download. We are also importing matplotlib and cbon again. Now, this is basically a 2-line code to train the decision tree. You can see that it's so simple the way it's written here, but as we have discussed in this course, if you really want to learn how decision tree works, you can actually write your own code, right, to do this, and it's not very difficult. Of course, we are not going to do that in this course because there is a lack of time. We want to focus more on applications, but I strongly encourage you, if you are interested, to actually write down the code for a decision tree yourself, and then perhaps even to train it by writing your own gradient descent code, but for now we will just be content with writing this Python code which takes care of all the coding for us. Okay. So, now how do you characterize the accuracy of a decision tree? You know that you can calculate the accuracy score, which is the proportion of the correct predictions over all the predictions made, and it is a simple and widely used metric for classification, especially when the classes are balanced. So, when you have roughly half of one class and half of another class in the training and the testing data, you can just use the accuracy score. However, if your classes are imbalanced, then you have to either stratify your train test split, or you have to use the balanced accuracy score. So, the accuracy is simply true positives plus true negatives divided by total number of predictions, and in the data set accuracy gives a quick measure of how well the decision tree is performing. We can also compute, as you have learned in the lectures, a balanced accuracy score, which is half the true positive rate plus the true negative rate, but in this case, since we have carried out stratified sampling, the balanced accuracy score will be close to the regular accuracy score. So, I encourage you to write the Python code to find the balanced accuracy score and actually convince yourself that it is close to the full accuracy score in this case. Okay. So, it is easy to actually extract the accuracy from Python itself. There is commands to do this. You can write your own code, of course, if you want to learn more deeply what is happening here. Okay. So, we find the decision tree accuracy to be 83%, which is not so great. So, out of all the predictions made, only 83% are good. One could say that it's a great number, but in case you want accuracy scores of 95 plus, then of course this is not a good performance. So, like I had said earlier, we can generate what is known as a classification report, which includes things like precision, which is the proportion of the predicted positives that are actually correct, the recall or the true positive rate, also known as the sensitivity, which is the proportion of the actual positives that were correctly identified. You can also look at what is called the F1 score, which is the harmonic mean of precision recall, and by taking the harmonic mean you are balancing out both the metrics, and especially useful with class imbalance. Okay. In this case not so much in our data set, but in other data sets this may be important. And finally, we also include support, which is the number of true instances of each class in the data set. So, this helps us understand not just the overall accuracy, but also how well the model performs per class. Okay. The other types of metrics that you can get is of course the ROC AUC score, that is the receiver operating characteristic area under the curve score, and we have already discussed that for a random classifier the ROC AUC is 0.5, for a perfect classifier ROC AUC should be 1, and as close as 1 as you can get is excellent. Okay. So, now this is how you can compute your accuracy, right, of the ROC AUC, the F1 score and the accuracy, and of course this is not cat boost accuracy, this is just the simple decision tree. So, you can actually cut this out here. Alright. So, the accuracy, and let us also remove this here. This is just the accuracy of a decision tree because that is what we have trained is 83%. The F1 score is around 0.81 and the ROC AUC is around 0.88, right. So, this is the classification report that we obtained. We have precision which is only 78% for non-metals, 90% for metals, recall is only 75% for metals. So, you can see that the model is not doing as well. So, next we will shift gears and we will cover the following bagging and boosting methods, including random forest, gradient boosting, XGBoost, light GBM as well as cat boost. Alright. So, what we will do is we will end this particular tutorial here, and in the next tutorial we will continue our exploration of boosted methods like XGBoost, light GBM and so on, and then we will have a segue to support vector machines and finally we will talk about Gaussian process regression. So, I hope you learned something new in this tutorial. Thank you for joining and I look forward to seeing you next time.